All right, so welcome to the University of Texas at Austin and our class on real-time digital signal processing. It's a hands-on class with a lab component and a lecture component. So a bit of a overview here. The slides are also online, and we'll have the links to that where you find the video. So links are back to my website. So I got a few things to cover for the class details and about the TAs and myself, and then what the class has in store. And please fire away questions as they come up. So this is material that's already on the course descriptor, which I handed to you. This is just a slide version of some of the same material. All right, so the class says 3 hours a week of lecture, 3 hours a week of lab. We'll have a few homework assignments, 8 of them in total. We'll talk more about that in a bit. My own background is in communication systems, image processing, and also embedded systems. We'll talk more about that in a second. And my office hours are going to be right after class, Monday, Wednesday, and Friday. And then for homework, which we'll have due on Fridays at 11 as you walk in the door, we'll have that. Have office hours on Thursday afternoon, and then the TAs, as you'll see, fill out almost the rest of Thursday afternoon and evening. And then also Mr. Jha has office hours on Friday morning for those last-minute questions. So the coffee hours are going to be at the cafe right over here. I'll mention it since we're online. I won't tell you which one it is. We'll wait till we stop the recording. But it's the one right closest over here by on the way to Double Dave's and so forth on San Jacinto. So the TAs here, Mr. Jha has TA'd, I think, 4 times before, and Mrs. Sino's TA'd once before, so both are experienced. We've got 4 lab sections, so you'll meet them through your lab section. I'll have them come Friday and introduce themselves and what they're doing in research. The office hours here, again, with Friday homework being due at 11. Thursday's a big day for doing homework, but don't start it on Thursday. Please start before Thursday. We'll be happier. But on Thursday, we've got office hours from basically 12:30 to 2:30 for me, and the TAs have it collectively from 3:30 to 7 p.m. And they're in ENS 137. It's not shown here, but it's on your handout on the course description. Also, we got office hours on Wednesday afternoon, and I've got them right after class on Monday, Wednesday, and I'm always available by email. So hopefully you'll start the homework. There are usually 3 problems on homework. There's 4 problems on homework 0, but 3 otherwise. But good idea to try to do at least one of them before Monday, just in case you have questions. And the homework will get you ready for the laboratory and also get you up to speed as we go toward the midterm number 1. There's also a grader for homework, and that's not either TA, that's someone else. And I'll let that grader be anonymous. But someone else will grade the homeworks that you turn in. So my own background, I've done a lot of work. This is the 26th time I've taught the class. This is a fun class. I introduced it back in '97 and continue to develop it. I have a lot of fun with this class. It ties in very well to the research that I do and that I continue to do. So this is some of the past projects that I've done with lots of students. So it's a big group of PhD and master students and some senior design students as well on some of these projects. So what ties into this class is basically all the way down to this, except the last row. And these different topics I'll bring into lecture as we get to them. So the first one is basically the first set here of communication systems. And in communication systems, there's a lot of signal processing, a lot of processing of signals to make the quality better, make the bits more reliably decoded in communication system at the receiver. For other applications like audio, we want the audio to sound better. We want the image to look better. So we'll talk about signal quality throughout the class and talk about algorithms that will give us different signal quality for the application that we're interested in. The last lab in particular will be an audio lab on guitar effects. That's where the audio will be first and foremost. The image processing will be scattered about in homework and in lecture, and in some demonstrations in lecture. Okay, so for the communication stuff, which is the first bit here. So for DSL, which is now pretty established technology, and this was really something I did back in 2000, 2001. This was a big issue, which for a little bit of signal processing, the companies were hoping to improve the data rate to the consumer you, me, whatever at home. And with a little bit of signal processing, we were able to show that in software only, with a software change, we could double the data rate for DSL modems without a change in the hardware. So some companies picked up on that and put that into their product line because they didn't have to change their hardware design. They just have to change out the software, they double the data rate, they beat their competitors. So that was kind of fun work. And the funding here is shown on the right, the companies that funded the work, not necessarily the ones that deployed the final result. Did some work in base station design. This is in what is now LTE, and WiMAX is something here in Austin done by Clear and Time Warner. LTE is your cell phone, your smartphone today, how you get data in and out of the cell phone as well as voice. So there's an issue here also of how do you improve data rate for each user. And again, we showed with the change of software we could, again, basically double connection speeds. Did some work outside of the consumer space, underwater communications for military applications, using a very large receive array of hundreds of elements, and we were able to show a massive increase, about 30x in data rate underwater versus a single receiver. So that's in communication systems. In image processing, it turns out it's the same kind of processing. It may not look like it. It's the same kind of difference equations and filtering and convolution. It's the same things you've seen in signals and systems, but just applied to a different kind of signal. So we, again, using some signal processing ideas with efficient implementation, we're able to improve things like image acquisition and image display on handheld devices and also image half-toning, which is printing. So we're able to work with a number of printing companies and smartphone display companies to improve, again, the quality of the image or video being displayed or printed in the case of printing. So those are completed projects, some new projects, and again, I'll take some ideas and measurements, and I'll have someone.
But what do we do?
Hey, Jack, I think we have some feedback from the speakers. There is another room listening to this downstairs in 2.146. I don't know if that was from the room. So also here in Powerline, this is basically smart grid communications, getting information from the home back to the utility to better allocate energy and to also charge us an appropriate rate based on usage. Wi-Fi, which is pretty much what we use day in, day out, how to get better connection speeds. We're working on that as well. And also, again, back to cellular, trying to improve some base station again, increasing connection speeds. And lastly, we've got some nice work in removing jitter or rolling shutter artifacts when taking video by smartphone. And we've got some very nice approaches for that. We have currently in that lab, and we're developing a unit for that right now. So getting rid of all the motion artifacts, which is really a blurring and a nonlinear distortion. We'll talk about that later in the class. It's an interesting problem to work on. Okay, so in all these cases, the students that I worked with and I brought our ideas, the algorithms we developed, down into some embedded prototype for usually for some release on the internet to let other companies kind of decide if this is useful. These are prototypes. These are not really meant for sale or for immediate commercialization. It's just, hey, this can work, and we can make it work in a cost-effective manner, either in hardware or software or both. So this particular class is an embedded software class. We'll also talk about a little bit about hardware trade-offs as we go through this. It's mostly software, a little bit of hardware as we go through. All the design works in software. Okay, so for the class now, what I wanted to do is define some of the terms that are in the title of the class. And I try to cite references as much as I can. So this is one from Professor Pat, which is here, who's here at University of Texas. And his definition I liked a lot. This is over just coffee with him. Basically, guaranteed delivery of data by a specific time. And this is a hard deadline. This is not I make it. It's not I make it 95% of the time. It's I make it 100% of the time. So this hard deadline is what we're going to talk about in this class. There are other concepts of real time known as soft deadlines, where you might say, I just want to guarantee data to arrive at a certain time 95% of the time. That may be good enough. But for our case, it's going to be a hard deadline. It's going to be a hard deadline real-time system.
You can email construction really.
Signal processing, lots of definitions out there. So I went to the IEEE Signal Processing Society to figure out how they define it, and I picked off these sub-bullets from their website. And some things may be pretty common, I suppose, things like generating information, generating audio, generating, perhaps synthetic video sequences through graphics. These are kind of maybe obvious things, maybe not. Maybe some things that are not so much obvious, which is extracting useful information from a signal or interpretation of the information. Now, extraction we're going to do a lot of in this class because we're going to be dealing a lot with communication systems. We're going to be extracting bit patterns from a continuous time analog waveform. We're going to be extracting information that was sent to us by a transmitter. Interpretation, we won't do so much of, but an example of this might be what? Can you think of it? I'll ask you this. Can you think of a way you might interpret information automatically by computer?
So if they don't.
Go ahead.
Maybe like, let's say you have like an audio signal, like music or something, you can decompose it.
All right. Yeah.
Outside of this room, we've never been asked questions.
So transcribing a performed or a piece of music that's being played into sheet music with notes and rhythm and so forth. Very difficult problem, but very interesting one. Can someone give me another example? That's a good one. Another example of interpretation. So digital communications, and how are we interpreting? It can also be extraction, but what interpretation would you do?
For if you had discrete packets and you're just waiting, you just in the packet when you need, so you have a header to notify them saying, hey, this is a message and the rest of it. So it's just for that happens.
Excellent. Yeah. So the communication side of that is we're going to extract bits from a continuous time analog waveform. A higher level processing which comes after that is, okay, what do these bits mean? What is the interpretation of these bits? It could be a header of a packet or a payload of a packet, and then I want to take that and assemble my packet based on that interpretation. That's exactly that's a good example. Lucia. Sure, absolutely. Face recognition, big topic right now, and certainly one. There's no end to whether it's a 2D image, still image, it's a video sequence, it's a three-dimensional capture, lots of interesting applications. Okay, so these are the kind of the purposes, I suppose, of signal processing. And then the next step is, well, let's come up with some algorithms to figure out how to achieve these goals. And ultimately, we have to implement them somehow on either for desktop simulation, and for us, we'll use MATLAB in this class, which is common in use in industry. And we'll go farther than that and say for certain of the algorithms we develop, we're going to go ahead and implement them in an embedded board. And that embedded board will have a digital signal processor on it. We'll program that in the C language. We won't program in assembly. As valuable as that is, we're going to take a little higher level view of the embedded implementation. And then finally, we'll talk more about specific applications during the class. We'll talk about speech processing, audio processing, image and video and communication systems, and a little bit in biomedical instrumentation, because there are some BME students in here as well. So now, an embedded system, lots of definitions. So I'm going to put up two here for you. These are, again, it's a huge field. So for me, an embedded system is something that performs an application-specific task, and it's often working behind the scenes. Now, that isn't always true. Sometimes the consumer has direct access to the embedded system and can actually program it. That can happen. Apps are a good example of that. You can control some of the embedded components inside the smartphone. But again, so this is a definition, and you can always blow holes through any definition, I think. So here's, again, my view. So an example here is speech compression. When you're talking on the phone, you really don't care about how that compression is being done. You just want it to be done well and get good voice quality. And it's up to the embedded system to worry about compressing the waveform, packetizing it, getting it over the connection to the base station, and eventually off to the intended user. So for us, this is pretty much the approach I'll be taking. But I also know this is not exhaustive as a definition. It's a working definition, maybe is a better way to say it. All right, so let's talk about the course overview. We're not going to be heavily mathematical in terms of we're not going to prove theorems in the class. We will do some derivations using the theory that you've learned in signals and systems. And in the second half of the class, we'll bring in some probability concepts, but not until after spring break. That's later. So the objectives here is to build intuition for signal processing concepts and to explore the design trade-offs in signal quality versus the implementation complexity. And I'll ask you some thoughts about both of those in just a second. So yes, we're going to use quite a bit of math to get there, but we're not going to be, again, proving theorems. We'll do some derivations. Mostly, again, reuse what you've seen before, go a little bit deeper based on your signals and systems background. So lecture here, you got 3 hours per week. We'll do these 3 concepts, or 3 topics, I suppose, in some detail. We'll spend the first half of the class mainly on the digital signal processing side. The second half is mainly on the digital communication side. And what will pervade the lectures will be architectures for actual implementation. They'll show up here and there. And there'll be a couple of dedicated lectures for that as well. The lab component, again, which is programming in C, you'll start in MATLAB, in the lab, have some MATLAB code as reference, and then try to implement C code given a lot of the skeleton of the program. So you don't have to worry about initializing interrupts and all. All that'll be done for you. You just have to fill in the main part of the C code. So for the laboratory component, we'll translate DSP concepts into software. We'll design implementation. We'll design and implement a real-time data transceiver, and you'll test and validate that implementation. So here's an example of, on the right here, measuring signal quality and implementation complexity. But before I do that, we'll get your opinion on what are some ideas of signal quality or some measures of signal quality. Go ahead. Classic one is signal-to-noise ratio. And this would be the, a definition here would be signal power over noise power. And then we can also convert this to decibels if we want to do it using a 10 log 10, and we'll talk about that. But now, this is nice. It's a nice starting point. It's the typical starting point when measuring signal quality. It's not usually the final step, but it's the initial step. What else can you do with signal? What other measures of signal quality are out there? And you may not have seen this before. SNR is not in any of the prerequisite classes, so if this is new, that's fine. Okay.
I forget the exact definition, but there's also a dynamic range,
Mm-hmm.
which I think is very similar to SNR, but we're measuring different.
Right, so there's dynamic range, which you can relate, and we'll relate this later in lecture 8. That is really poorly written. Well, I'm going to put it down here. There we go. There we go. Dynamic range. All right. So dynamic range can be described in terms of voltage range. It can be described in terms of SNR. It can be a function of frequency. Lots of things here. And we'll talk about dynamic range as it relates to SNR again in lecture 8 on quantization a little bit later. What other measures of signal quality? Just think of how you like or don't like products that you use. How would you define signal quality? Go ahead.
Amount of bandwidth.
Amount of bandwidth, absolutely. Bandwidth. And we can take bandwidth and relate that to bits that we can communicate. There's a direct relationship. But there are other ways we can think about bandwidth. It doesn't have to be a digital communication stream. What else is there for signal quality? Go ahead.
Or probability that there will be an error, maybe like bit error
Yep.
probability.
So in a communication system, it's the probability. So signal quality is the probability of correct detection. Probability of correct detection. What's the likelihood that the bit that we received, and we then extract an estimate of that bit, is it 0 or 1? How often is it correct? And we like it to be correct all the time, but unfortunately, there's always noise and other impairments. We won't be right all the time. There's some probability of making a mistake. So that's another measure. So for the application of communication systems, this is a very important signal quality measure, which we will relate in terms of SNR a little bit later. It does relate to SNR for the case of what we call single carrier communication systems. These are communication systems that are operating with one carrier frequency. Okay, so these are 4 different signal quality measures. It doesn't have to stop here. You can generalize SNR. SNR right here is just is simply a number, the way I've written it as a definition. It's signal power over noise power. You can also talk about SNR, or signal to noise ratio, as a function of frequency. So different frequencies could have different SNR, I suppose, results or measurements. And different, so in the case when different frequencies have different degrees of importance, this matters. So in audio, we don't hear all frequencies. Normal hearing is roughly 20 hertz to 20 kilohertz. The SNR that we care about is in that range. We don't really care about it outside of that range. And furthermore, our auditory system is not a flat response over frequency. It has a shape to it. Okay, and we have a peak around 1 kilohertz in our hearing in the low-level processing of our auditory system. So we can also think about SNR as a function of frequency, or if you prefer hertz, we can talk about SNR as a function of frequency in hertz, omega in radians per second, or F in hertz in terms of continuous time frequency. So lots of measures out there, and that's where we go. So for audio and image and video, we will generalize the notion of signal-to-noise ratio to be dependent on frequency, and then use the way our human system responds to visual or auditory stimuli to know what shape we care about, what's the relative importance of different frequencies. And that's known as weighted SNR, and we'll talk a little bit about that a little bit later. That's in not until sampling and aliasing. We'll do that a little bit in lecture. Again, it's actually lecture 8 on quantization. Is when we talk about that. That's after spring break. All right, but before spring break, what we're going to use is SNR as our basic measure and go from there. And then again, we can extend this notion in lots of different application directions. All right, next one is implementation complexity. What are your thoughts on how to measure the complexity of an algorithm implementation? There's some things to care about.
Well, we could probably take a look at the time complexity and also maybe the magnitude of the pole. Magnitude of the poles in a digital filter.
Oh, that's very specific for the filter, but more generally, execution time. How long does it take for the algorithm to run? And clock time, wall time, whatever. What else do you care about in terms of implementation complexity?
Memory needed.
Memory needed. So I've got memory usage or footprint. Right? How much memory do I need to store both the program and the data? And what else? Let's relate it to memory. So that's how much memory I need to allocate. But there's another issue that I have. Yeah, the hardware to support it, because I also care about getting data to the CPU at some rate. So I have 2 issues. I have to get data off the chip onto the chip, and vice versa. And once the data is inside the chip, I've got to get it to the CPU to do some work. So I've got hardware issues on memory I/O. So memory I/O rates becomes very important. Again, with hard real-time systems, we want to guarantee data getting off-chip to on-chip in a reliable manner, working on that data and getting it off-chip to meet a specific deadline all the time. Okay, so there's a lot of hardware support to make that happen, and we'll talk about that as we go. Okay, what else can you think about implementation complexity?
Lines of code.
Lines of code, absolutely. And that's going to relate to also memory usage, where how much do we need to store. So lines of code. We can keep going all day, I think. How about power consumption? Physical volume, physical area. There are lots of things to worry about here. So there's power. physical volume, and area. Lots of things. Okay, so for this class, we're going to be concerned about execution time, memory usage, memory I/O rates. So we're going to focus on. And we can relate these, of course, to other things here, power and so forth. Okay, so here's an example on the slide showing some work a long time ago in DSL. So it was, the formal name is asymmetric DSL, but as far as the consumer is concerned, it's just called DSL. Well, it turns out there are multiple kinds, but the one to your house is ADSL. So this was a trade-off where this is the kind of analysis I hope you can do it by the end of the semester, not now, but by the end of the semester, given a couple of algorithms, maybe 3 algorithms, here I show you 7, what is the trade-off between some measure of implementation complexity and some measure of signal quality? Now in this case I've gone with, for the implementation complexity, I'm only using the number of multiplication operations, total multiplication operations, to come up with the coefficients for this filter. There's a filter in here, which is an equalizer. All this really does is correct for frequency distortion in the channel and analog front ends. We'll talk. That's actually not until the last homework assignment coming up. But it's just a filter. It's a difference equation. We have to come up with the coefficients for that difference equation. So in the field, the receiver spends some time figuring out what this coefficient should be, and it needs this many multiplies based on which of the 7 algorithms that I'm going to look at. Each of the algorithms has a different amount of signal quality, and the signal quality here is the data rate supported, or the bit rate supported in megabits per second. So it's a little hard to read here, but this is 6 megabits per second. And this is 5.9, 5.8, and so forth. So they're in increments of 0.1 megabits per second. So if you were to look at this, one of the reasons to do this trade-off analysis is to figure out which algorithms really are not practical for an implementation. So let me ask you, so this one is a low data rate but has low complexity. That might be useful if I want to reduce my cost. This one has much higher data rate, 6.4 something megabits per second, much higher computational complexity. And that might be useful in the central office for a telephone company, maybe, don't know. Now what would you say about these 5 algorithms? This is where it gets interesting. What would you say about this group? And you can eliminate as impractical? Farthest right? So in fact, they give all about the same data rate. They're all about 6.2 megabits per second. And this one you want to eliminate, which makes sense to me. It's more than 10 times the complexity, and I'm really not getting very much improvement in the signal quality in terms of bit rate. So why would I spend all this extra effort for such a marginal improvement? And I can apply the same idea, get rid of all those. So now I'm down to 3 choices that are practical. I have a low data rate, low complexity, a medium data rate, medium complexity, high data rate, high complexity. 3 reasonable choices, 3 good design points to choose from in my final design. I'll pause for questions. There's a lot of stuff. Always fire away at questions as you get them, but I'm going to just pause anyway here. It's not till the last week of lecture. Okay, so you got a long way to go before we get to this point. Let's talk about prerequisites and co-requisites. Now, as advanced as the technology is at the University of Texas at Austin, in our department, we manually check the prerequisites. We do not automate, although we could automate it. The option is there in the registration system. We have chosen not to automate that. Okay, so just to make sure that you've got the prerequisites coming in, okay, so it's 3 classes of prerequisites with a grade of C- or higher. And I don't have the UT numbers, but if you remember, this is going to be EE 312, EE 319, so this is 313 or BME 343. Right. This one's 319K. This one's 312. This one is, I always forget the BME, 350, 350, 335, there we go. Thank you. So you can take probability at the same time because we won't use probability concepts until we come back from spring break. So it's okay to take them concurrently. We haven't had trouble with that in the past. And then this is the engineering communication course, technical writing as a prerequisite. So if there's, hopefully this is good. If there's any, okay, feeling good. Now, my hope is that your experience was good in all of these classes. And if they weren't, if you had a bad experience, my hope is that this class will help you turn around and appreciate all that stuff that you maybe didn't like back then. Maybe you burned the textbook. I don't know what you did, but let's hope you have a better experience too. Okay, some detailed topics related to those classes. For signals and systems, lots of stuff we're going to use. It's probably the material we're going to use the most is from 313 or BME 343. So it's going to be, and we're going to review this. We're going to spend 4 weeks reviewing this material in lecture. We have 2 homeworks to review this material. It's been a while. It's okay. So we're trying to get it back into our comfort zone. So again, for the topic of digital signal processing algorithms and applications, we got signals, convolution, and sampling. This is how filters work in the time domain, convolution, very important stuff for linear time invariant systems. In the other domains, the Fourier domain and the generalized frequency domain, we have other ways to analyze filters and systems, linear time invariant systems. What we haven't, which you may not have seen, I don't expect you to have seen, is filter design and implementation. And even though we talked about signal-noise ratio already, I don't expect that you have seen that. It's okay if you have. I'm not expecting you to have seen that. I expect that from your embedded systems course that you've seen some measure of quantization. You're back in 319K, you had a microcontroller. You took data from the physical world into the board and to the chip, and you sent signals from the CPU off the board. So you had to deal with some notion of quantization. What was the data converter in the 319K class? How many bits? 4 bits? Quantization?
I don't think it was. I think the DAC was 4 bits.
The ADC was like 8, 10.
Right. They do. So the analog to digital converter was 8 or 10 bits,
Yes.
and the digital to analog converter was 4 bits. Okay.
So we built it like with an R2R ladder.
So you really know. You really, yeah, good. Okay. So in our case, we won't have to build it. We'll use what's on the board. It'll be a 16-bit D to A and a 16-bit A to D. And we'll talk. So we'll be able to read 16-bit ints. Okay. So for the second topic, digital communications and algorithms. Oh, we'll talk a lot about how data converters are designed. I'm glad you've already done one, but we'll talk about it in more general terms and how you might do this in a hardware design for high-speed data conversion in lecture. All right, so the digital comm side, build on some Fourier transform knowledge from signals and systems, multiplying by cosine in the time domain. This is the analog modulation property in Fourier transforms. I don't expect you to have seen digital modulation, but we'll do this all in discrete time in the lab. All be done in software. So we'll talk about how to make the jump to discrete time. And this is nothing but a filter. It's pulse shaping. And pseudo noise is a way to generate noise that looks like noise, it sounds like noise, but it has a periodic structure that we can take advantage of in lots of different ways, for test, for measurement, for communication systems. Extremely useful. That's lab 4. Now, signal quality, the 2 big things we're going to focus on are going to be signal to noise ratio and different variations of that, and the probability of a bit being incorrectly decoded at the receiver, the bit error probability. We'll talk about this. We'll derive this. It won't be so bad to derive it. Gaussian, well, it won't be too bad by the time you come back from spring break. And then we'll simulate a lot of this using MATLAB to see it in action. For the architecture side, We'll talk about the assembly language of your processor. You'll look at some assembly code in Lab 3, but you won't write any. Unless you really want to, but you won't be required to write any. As valuable as it is, this class is already pretty overloaded, quite frankly, as it is. We'll talk about interfacing the board to the physical world, talk about pipelining in the CPU core itself, and some interesting features that make these kind of algorithms go fast. Harvard architecture is one of them. And this is the idea to have separate program and data buses and dedicated hardware to support that, and dedicated addressing modes for that. There are also some special addressing modes to speed up things like filtering. We'll talk about those through lecture. And some of the hardware support for real-time programming in a digital signal processor. And a lot of those concepts have carried over into general purpose and other embedded types of processors. Okay. Here's some DSP processors and products. Lots of different products out there. This is a big market. It's somewhere around $8 billion market a year. It's not, which is pretty extraordinary. So it's one of many embedded processor families out there. And in these days, a lot of this is embedded on a single chip with other kinds of embedded processing cores. It's rare that a DSP is the only embedded processor in a product today. Although sometimes that happens. In the smart meter case, that does happen for the communication system. But usually the DSP is working in conjunction with an ARM or some other processor inside the product. So the whole space of consumer audio, pro audio, image and video, multimedia, and communication systems. Your particular processor is targeted for consumer audio and pro audio. In fact, these are C6000. So your family of processor, you'll be using the C6000 from Texas Instruments. This processor, many of these are actually products are using this processor. This was originally designed for consumer audio and pro audio, and later extended, actually, it's not true. Initially it was for communication systems, later it was extended to consumer and pro audio, and it's a multimedia system. We'll talk about that as we go. But your particular processor is a 6748, which is a floating point DSP, 32-bit processor with 32-bit float as one of the native data types, which is ideal for audio processing. We'll talk about that as we go further in the class. It really is a 3. Okay, let's try this again. 32-bit floating point data and arithmetic built in. Also has 16-bit fixed integer arithmetic, 32-bit integer arithmetic, and so forth. But in class, we're going to do everything in floating point. It's just easier. It matches what we do in MATLAB. Just again, it's just class is already full with stuff to do. So we're not going to worry about converting to fixed point in the lab. We'll talk about it in lecture, but not worry about it in lab. Okay. All right. There is a smartphone family that uses this processor. I think it's the Motorola. It's a Motorola smartphone that uses this TI family under the hood. But most of its use right now is not in the smartphone market. It's in these other consumer electronic product lines. But again, the ideas that you learn are going to be more general than this particular processor. Okay, so here's the required textbooks. This is both the lab manual, which is the bottom one, and the textbook, which is the top one. So the textbook is software receiver design. This was the lower price of the two books. It's design of digital communication systems, lots of MATLAB code, about 140 MATLAB programs in the book, typed out for you. Don't retype them. They come as a zip file, and the homework page has that download information. But in homework, we're going to take the existing MATLAB code and slightly modify it and try something out and see what happens. So there's going to be a lot of MATLAB-based homework, starting with homework 2. Homework 0 and 1 is mostly paper and pencil, a little bit of MATLAB. But by homework 2, we're going to be heavy MATLAB. We'll get there slowly through lab and also through lecture and through homework to get up to speed on MATLAB. Okay, the book, the lab manual, is pretty good at showing you the basic theory for each lab assignment, the MATLAB code that goes with it, a demo that runs on the board, and then finally what you have to program. There's 3 steps in every lab, and you'll see the MATLAB code prior to seeing what you need to do in the C programming that you need to write, or the C programs you need to write. So a few things on the side. So Rick Johnson, Bill Sitharis, Sandy Klein are all amateur musicians, still have their day jobs. So Andy was bass, Bill's keyboards, Rick is drums, and I have seen them play in their basement. And they have fun, but they're not going to be touring, I can tell you. But they're good. Cameron Wright is a UT grad. I'm going to highlight that there. Kind of cool. So he finished in '97 with his PhD here in the department. I was not his advisor. I wish I were, but I'm not his advisor. And so these are the 3 folks that deal with the lab component. So if you see errors or you have suggestions, you can write to them directly if you wish. I'm pretty open to constructive criticism. Did anyone have trouble finding the books? Not yet. Okay, there's some optional books out there, and really I'm not going to require any of these, but you may already have some of them from other classes. I'll be running lots of demos from this particular book by Jim McClellan, Ron Schaefer, Mark Yoder. And these demos are all online, so you don't need the book to run the demos. And you'll see these names later you'll see his name a lot in filter design. We'll talk about that a little bit later. And then Ron Schaefer wrote a really excellent book to establish this field of digital signal processing theory back in '75. He's now retired from Georgia Tech and works at HP. Jim McClellan's at Georgia Tech, and Mark Yoder's at a school called Rose-Hulman Institute of Technology. The book you may have seen you've probably had one of these 3 books in Signals and Systems. You either had Lothy, Roberts, or Oppenheim and Wilsky. Not sure which one you had, but how many had Lothy? I'm just curious. How many had Lothy? So almost everybody. Roberts? Nobody left for Roberts and Oppenheim and Wilsky? The 2. Okay. So whatever book you're used to, use it. Right? So because you're familiar with it and all of its where to find things, how to use a table, whatever, what's in the glossary and so forth. You're just familiar with it. So I would, if you still have it, use it. And if you don't have it, maybe find a copy somehow, somebody, just because you're familiar with it. There's a free book online, and I have met the author, Steve Smith. He's a very dedicated guy to this idea of putting stuff out for free. The whole book is available for free. It's pretty cool. You can also download chapters if you prefer. And it's dspguide.com. Again, it's written in '97, so the topics on digital signal processors will be a little bit out of date. That's just a few chapters. The rest of it's very much up to date. And it's free. All right. Now, probably the last slide for today is my guess. We'll see. Is how this class relates to other classes in the EC curriculum. And if you're a BME student, these classes may still be of interest to you. And I kind of point them out at not only kind of where it fits in, but also talk a little bit about workload, which we'll get to. So there are 3. These are older technical core names in our department. These 2 are now combined into one technical core. So it relates, so this class, Real-Time Digital Signal Processing Lab, it relates to the DSP theory course, which is offered every semester. Introduction to Data Mining, which is once every other year. Image and Video, which is every fall. And on the communication and network side, it relates to Digital Communication Theory, which is once every 2 years in the spring. Wireless Communication Lab, which is every fall. And Telecommunication Networks, which is, I guess it varies a little bit, but typically in the fall. Okay, so this is the class to take to interpret the bits, to figure out what's the packet header, what's the payload, and all that. That's this class. Wireless communication lab is the one that takes what we do in the lab and make it wireless. So our connections in the lab will be all through wires between transmitter and receiver. The wireless comm lab makes that connection wireless in the lab. This goes into deeper theory than we're going to have time to go into. Maybe 30% overlap with this class, but a lot more. Here you would derive the more derivations and proofs of theorems. This is more detailed in this topic. Now, so this is more the application theory side. On the implementation side, there are a number of possibilities. Embedded in real-time systems, which is 445M, right? That's some of you are in that now. And this is the FPGA course, 460M, CompArc, which is 460N, and then real-side design, which is 460R. So these are all really nice complements to the application theory. We're going to do both in one class. We'll talk about the application theory and how to map that into embedded software. So now my question, what's the course with the highest workload at UT Austin on this list? Computer architecture and yeah. So I asked Professor Pat one time, what's the workload in there? And he thought about it for a minute. He was in my office, and he turned his back to the board, and he wrote that. Okay. Tongue-in-cheek, but the reality is whatever you can give it, he'll take. Okay, which is fun. It's a great class. You get a lot out of it. But it's just worth figuring out, is it, with other classes you're taking. So I would put this at 30 hours a week, to put it a little bit more quantitatively. Next highest work, and this, by the way, if you look at the course evaluations that you turn in, there's a rating called workload, and there's excessive workload, above average, whatever. So this gets 50% excessive workload rating from the students. So you have spoken in the course evaluations to say this is the highest workload. It has the highest excessive workload rating of any of our classes. Okay. What's number 2 in here? What's your guess? You're very close. It's a tie. I'll give it. This one and turns out this one. So you get about a 45% excessive workload rating from the students. So these weigh in at about 25 hours a week, my guess, my estimate. And the rest, again, there's some variability. You could say 15 to 20 based on lots of things, other prerequisites you've had and so forth. But taking all these 5 together, what do you think? Good idea? Pretty exciting idea, yeah. So, so think about what you're taking this semester. It's going to be these are all great classes, but just to make sure that it's not overloading. The rest of these workloads are not too bad. This is probably 10. This is 50. Actually, this is 20, I think, these days. And this is probably this isn't being offered right now. And I don't know because it's an instructor that's new. He's not new to the field. He's a very famous guy in the field. But I don't know. It's the first time teaching at UT. And this is probably 20. And that's probably, I think, somewhere in there. So it's just to think about this semester. You want to have a good, rewarding semester, time for things like looking for internships, full-time positions if you're graduating. That's a feature of my elbow. Okay.
It's back on.
Oh, good. Great. We'll play games with it. All right. Any last questions before the time is up? Got about a couple minutes here. Go ahead.
Are we going to need anything for the lab? Like, should we bring our laptops or anything like that?
For lab, we'll be using ENS 252B, and labs do not begin until next Tuesday, the 21st. Okay. So we have PCs already there, desktop PCs, already have the software on it. You check the boards out, at the checkout counter. So you really won't, but if you want to bring your laptop, that's fine. If you're more comfortable with it, you like your version of MATLAB, whatever, no problem.
But it's not necessary.
Not necessary.
We choose our partners at.
Yes, you choose your partner in lab. You won't have to do that until January 27th. But yes, you get to choose your partner in lab. Okay, thank you very much. See you on Wednesday.